All right, this is the final exam review for chemistry. Let's just review first what the day will be like. Make sure you get there early so that we can seat you. Otherwise, you won't have as much time to take the exam. So you need to get there fairly early. Seating will be a little chaotic, so you want to get there early and be seated correctly, because we have to separate each student, make sure there are rows so that the proctors can walk up and down the rows, across the rows. So that's the first thing that's very important. Next, make sure you have pencil and pen so that you have something to write with. You can erase. Do the answer sheet in pencil so that you can erase and it doesn't look too sloppy and it can be read conveniently. You're going to need a calculator. If you have a graphing calculator and you need batteries, make sure you have fresh ones. You won't be able to borrow a calculator. So if your calculator breaks or runs out of juice, you'll have to do without it. Secondly, you want to bring a calculator. If you don't bring a calculator, you can't use one because you can't borrow one during the exam, no matter what the situation is. You must have a calculator with you. If someone's taken your calculator, borrow one from someone. I will not have extra calculators there. Next thing you have to bring in one A4 sheet of paper, a sheet of paper written on both sides. Now that's for credits. That's part of your exam. If you don't have that, that section of the exam will be a 0, so make sure you have it. Secondly, you can bring in an additional A4 sheet of paper written on both sides, and that is going to be extra credits. That will be extra credit. And you will be given a periodic table. That's it. You'll be given the exam. You'll be given scrap paper. Then, when your exam is complete, you hand in everything. You hand in your cheat sheets, you hand in your answer sheet, you hand in everything. You hand in your question sheet, scrap paper, and then I give you a sheet of paper, one A4 piece of paper, and you write your reflection, making sense of the course, drawing connections, mind map, whatever you want to put, and that's going to be extra credit. So make sure that you practice that before the exam begins, before you get in there, so you have a good idea what to write. You will not be able to have a reference sheet to read from or to create your reflection from. You need to make sure you know what you want to say. Make sure you leave yourself enough time to do that. It's a 2-hour exam. You have 150 multiple choice questions. Many of the multiple choice questions are very simple, but many of you take far too long to think about each question. If you don't understand a question, leave it blank and move on. Don't overthink your questions. Don't overthink them. They're relatively fairly simple. Know your definitions. Those questions you want to answer within seconds. The ones you want to think about, you want to maybe leave until later on. Get some of the questions done that are simple. Then I collect your exam and you're done. And we still will have class, but just pay attention to the announcements and the schedule, etc. Okay, let's begin the review. I'm going to take each chapter individually, talk about each chapter, and then we'll look at questions from the book problems that I posted a few of them in sections on this review based on the chapters. All right, let's begin. All right, chapter 9 is first. I have in my hands the final exam, and I'm going to just look through the exam and see if I can find some problems relative to chapter 9. Okay, the first thing I see a matching section, and some of the terms that you should know. Monoatomic ion, that's like chloride ion, bromine ion, oxide ion, etc. Remember, when you're naming compounds, if it's a single ion in the negative ion, and anion, it's called IDE, chloride, oxide, bromide, fluoride, etc. If it's a polyatomic ion and as a negative ion, as an anion, you have to name the polyatomic ion like it's going to be phosphate. So sodium phosphate, not sodium phosphide, for sodium phosphate. So, and don't forget, if you have an individual ion in the positive component, like sodium, it's just named sodium. There's no suffix or prefix. So if it's NaCl, it's sodium chloride. Okay, so monatomic ion, acid, base. Remember, we introduced that in Chapter 9, acids and bases, even though the chapter we did was Chapter 619 on acids and bases. Law of definite proportions. We use that in stoichiometry. Law of multiple proportions, cation, binary compound, anion, polyatomic ion, etc. I'm looking at some other problems here. You're going to have to know some common polyatomic ions, but I'll go over that a little bit later. You will not have a polyatomic ion reference sheet, so if you want to put some of those on your cheat sheet, that might be recommended to you. You're going to have to know your acids, how to name acids. For instance, H2S is hydrosulfuric acid. H2SO4 is sulfuric acid. H2SO3 is sulfurous acid. So remember, in general, if you have a polyatomic ion, you say ate becomes ick and ite becomes us. So hypochlorite would be hypochlorous acid. HClO3, chlorate, so that would be chloric acid. Phosphoric acid, phosphoric acid. Phosphorus acid, H3PO3 is phosphorus acid. H3PO4 would be phosphoric acid. So don't forget your nomenclature. You're going to need to know Roman numeral system, for instance. Iron 3 sulfate. Iron 3 sulfate. If it's a transition metal, you need Roman numerals. Okay, if it's a transition metal, you need Roman numerals. Okay. If you have something like two nonmetals, you'll use the Greek system, for instance, carbon dioxide, carbon monoxide, etc. Okay, now let's go to Chapter 10. That's on moles, and see what we find there. All right, Chapter 10. Let's see what we have in Chapter 10. You're going to need to know, you have a little bit of a matching section. You're going to need to know, well, what does representative particle mean? Mole, Avogadro's number, which is 6.02 times 10 to the 23rd. Percent composition, standard temperature and pressure, that's STP. Empirical formula, how to get an empirical formula, how to use Avogadro's number. I will say much about the mole in later slides, and I'll give you some practice as well. I have practice problems for chapters 9, 10, 11, 12, 13, 14, and 15. I don't have them for 16 and 17 only because we just really did those, and there's book problems that you can access for solutions and acid-base chemistry. So I'm not doing a heavy review for solutions in acid-base chemistry. You just took the test on that. You may want to read that over, those lectures. I didn't get a lot of views on YouTube, and you're going to want to look at those. Okay, now, moles. All right, moles. You're going to need to know, you're going to know how to make the following conversions. Moles to mass, moles to volume, moles to the number of particles, and the other way. Number of particles to moles, mass to moles, etc. You're going to have to know to go from mass to moles to volume, from volume to moles to mass, etc. Okay, I have a little chart in the review that you may want to write down in your cheat sheet. I also have problems where you're going to have to go, for instance, here's one right off the test. How many atoms are there in 3.5 moles of arsenic atoms? Or what is the molar mass of aluminum pyrophosphate? So you count up all the atoms and you find the mass of the whole thing. So in other words, the mass in grams of 1 mole of any particle is equivalent to the mass of one particle in atomic mass units. You're going to have to know how to do empirical formula. I have an example later on in the review on how to do empirical formula. You can look that up on my book problems. You're going to have to know how to do percent composition, which is backwards relative to empirical formula. Given the formula, you have to know the percent composition. You have to, again, be able to do empirical formula, and that's about it. You're going to have to know everything there is to know about molecular formulas, how to get the molecular formula from the empirical formula, and that's about it. Okay, fairly simple. The mole, empirical formulas, molecular formulas, percent composition, moles, mass, volume. Remember, the volume of any gas at STP is 22.4 liters, for instance. And let's go on to equation writing. Okay, equation writing. Now, do I have a matching section on equation writing? No, I don't have a section on equation writing. I have a section on stoichiometry and solutions, but we'll get to that in a minute. All right, equation writing. Obviously, if you're doing equation writing, you're going to have to know things like the reactants, the products. You're going to have to know how to balance an equation. You're going to have to be able to predict products. You're going to have to know single displacement or single replacement, double replacement, synthesis, composition, and combustion reactions. Let's see what's on here relative to it. You're going to have to, like for instance, I'll give you a chemical equation, a stoichiometric equation, and you're going to have to balance it. And what they'll do is they'll give you all the coefficients. So you'll have to know how to do balancing equations, predicting products. So for instance, if I have a base anhydride and I add water, so I had magnesium oxide plus water is going to equal magnesium hydroxide, for instance. So you may want to write down some of the information I gave you on equation writing. Let's see, what else? Combustion reactions. That's where you have one of the reactants is oxygen. You have balancing, again, coefficients in front of the formulas. You have to know, maybe you're going to want to write down the activity series. That's going to be important. You're going to have to, here's one on double replacement reactions. Don't forget, with a double replacement reaction, you have A, B, C, D, yields A, D, C, B. You're going to have to know what is the reaction based on. That's the conservation of mass. Everything is always conserved. And reactants, products, and that's about it. Okay, so that's pretty thorough actually. But for instance, let me give you one question off here. It says, let's see. Let me give you one. Which of the following statements is not correct? A, the only way to determine the products of a reaction is to carry out the reaction. B, all chemical reactions are classified as one of 5 general types. C, complete combustion has occurred when all the carbon in the product is in the form of carbon dioxide. A single reactant is the identifying characteristic of a decomposition reaction. So you have to know which one of those statements is not correct. I won't tell you now. Okay, so let's do stoichiometry. All right. stoichiometry, and that's chapter 12. Okay, chapter 12. We have a matching section in the beginning: actual yield, percent yield, theoretical yield, excess reagent, limiting reagent, mass, number of molecules, volume. Down in the test, you're going to get, you need to know, first of all, you need to know your equations, and you'll be given equations. You may have to balance one, but you'll have to do stoichiometric operations. You'll have to, given moles, how many moles of one reagent will react with another reagent. You're going to have to know on your scrap paper, your stoichiometric masses. So if I have a reaction, for instance, write this down. CH4 plus 2O2 yields CO2 plus H2O. Right. Now, the first thing you're going to do, first thing I would do would be, I would say, all right, methane, 1CH4. So I would say 12 plus 4 times 1, that's going to be 16. So I put 16 above the methane. 2O2, so that would be, O2 is 32, 2 of them would be 64. I put 64. Carbon dioxide, 44. 2 waters, 2 times 18 is 36. So I put my stoichiometric masses. I would recognize that I have 1 mole of methane per 2 moles of oxygen, and that will yield 1 mole of carbon dioxide and 2 moles of water. So if it says, if I were given, let's say the question says, if I'm given 1 mole of methane, how many moles of water do you get? Well, 2. You just read that right off the equation. Or if I say I have a 1/4 mole of methane, how much water do I get? Well, 1/4 of 1 is 1/4. 1/4 of 2 is 1/2 mole of water. So 1/4 mole of methane would give 1/2 mole of water. So know your mole ratios that are inherent within the stoichiometric equation. And then you can do the same thing with the masses. So you say, if I have 20 grams of methane, how much water am I going to get? Well, I would say 1 mole of methane, 1 mole CH4 over 2 moles of H2O equals 16 over 36 equals the mass over the mass, etc. Know how to do all of that. Know how to do mass, volume, volume, mass, etc. Know limiting reagents, excess reagent. Percent yield. Know percent yield. What about theoretical yield? I said conservation of mass. What is the difference between percent yield and theoretical yield? If I have a particular reaction and I do a mass calculation, the answer to that mass calculation is the theoretical, is what I should get, is the theoretical yield. Then if I actually do the reaction and I get, let's say I'm supposed to get 100 grams of reactant, and then I actually do the reaction and I only get 80 grams of the reactant. The percent yield would be 80%. So it's what you should have gotten, that's the theoretical yield, and then you say what you did get divided by the theoretical yield times 100 is the percent yield. All right, so now let's go on to states of matter, chapter 13. Okay, chapter 13. Now, this one there's not a lot of material here. There is some, of course, but it runs kind of into gases, which is very similar in some ways. Okay, so you got to know the kinetic theory, elastic collisions, what are the spheres like, how do they perform elastic collisions, particles of a gas, what is the instrument used to record atmospheric pressure, what are standard conditions relative to kilopascals and Kelvin, what is boiling point, what is the relationship between boiling point and vapor pressure. What is the relationship between atmospheric pressure and vapor pressure? What controls vapor pressure? Especially relative to hydrogen bonding. What is helium have to do with hot air balloons? Is a hot air balloon helium, or is a hot air balloon something different? What's the density of air or any gas when you heat it? What is a phase? What is a phase? Metal, solid. What is the dynamics of the atoms in a metal compared to a gas? Are they moving at all? What's absolute zero? What's the relationship between absolute zero and the movement of atoms? What can you say about the movement of atoms in a big chunk of steel? Is there energy in the steel? Next, we're going to do gas laws, Chapter 14 on gas laws. All right, Chapter 14, gas laws. Boyle's law, pressure and volume are indirectly related. PV equals PV. Gay-Lussac's law, P over T equals P over T. They are directly related. Pressure goes up, temperature goes up. Charles' law, V over T equals V over T. They are directly related. Temperature goes up, volume goes up. And the combined gas law, Graham's law of the effusion or diffusion of gases. Partial pressure, Dalton's law of partial pressures. And that's about it. I'm not sure there's a lot more there. Don't forget, Boyle's law is indirect. I think I said that. Pressure goes up, volume goes down. And what is the relationship between moles and pressure? What is the ideal gas law? Why is the concept of ideal gas law a little bit weird, a little silly almost? And that's about it. All right. Now chapter 15, which is water and aqueous systems. In chapter 15, what is the relationship between hydrogen bonding and surface tension? How can I reduce surface tension? What is a surfactant? What are emulsions? What is a colloid? What is a suspension? What is a solution? What is a nonpolar solvent? What is a polar solvent? What does hydrogen bonding have to do with all of that? What is the difference between polar covalent, nonpolar covalent, ionic, network, solid, for instance? What is the relationship between molecular geometry and whether or not something can dissolve? Yes, this exam is on Chapter 9 on. However, Chapter 8 with molecular geometry, you're still going to have to review that because Chapter 15 has a lot of molecular geometry in it. And I went over a lot about molecular geometry in Chapter 15, so it's part of the deal. It's unfortunate. What is water of hydration? What are hydrates? How can I soak up excess water in a chemical using a hydrate or an anhydrous form of the hydrate? What is solvation? What does electronegativity have to do with any of this? Next up, solutions. Chapter 16, solution chemistry, concentration, solute, solvent, different types of concentration, percent concentration by mass, percent concentration by volume, molality, molarity, mole fraction, etc. What about colligative properties? What are the colligative properties? What are colligative properties really based on? Why do I use molality when I'm talking about colligative properties? What's the equation for freezing point depression, freezing point elevation? What is the difference between two substances? They both dissolve, yet one substance does not dissociate, the other one does. For instance, glucose dissolves, but it doesn't dissociate. Calcium chloride dissolves and dissociates. What's the difference between calcium chloride, CaCl2, and sodium chloride, CaCl? What is the relationship between boiling point and increased number of particles in solution? What is the relationship between freezing point and increased particles in solution? What is the relationship between hydrogen bonding and boiling point and solute, and what type of solute? Is the solute a solid or is the solute a gas? What is the difference between dissolving carbon dioxide in cold water versus dissolving carbon dioxide in warm water? What is a supersaturated solution? What is a saturated solution? What does concentration have to do with whether or not a solution is saturated, supersaturated, or dilute? Here's a question. To 225 milliliters of a 0.8 molar solution of Ki, a student adds enough water to make 1 liter of a more dilute Ki solution. What is the molarity of the new solution? Here's another one. Which of the following is an expression of molality? Which one is an expression of molality? How do I convert a solution which is percent by mass to a molarity solution? So how do I change a 5% solution by mass to a solution that is expressed in molarity? Okay, next up, chapter 19, acid-base chemistry. Acid-base chemistry will include pH, pOH. pH plus pOH equals 14. How do you calculate the pH? It's the negative log of the molar H ion concentration. The pOH is the negative log of the molar OH concentration. How do I write a Ka expression? I take an acid, breaks down to the H ion, plus the anion. So it's going to be the product of the molar concentrations of the cation and anion divided by the molar concentration of the acid. How do I find Ka? Well, I either find Ka plugging in the values of the molar concentrations of the dissociation of the acid, or Kw equals Ka times Kb, therefore Kw divided by Kb is Ka, Kw divided by Ka is Kb, Kw equals the molar concentrations of the H ion times the molar concentration of the OH ion. What is an Arrhenius acid, a Bronsted-Lowry acid, a Lewis acid, a Lewis base, a Bronsted-Lowry base, an Arrhenius base? What is a strong acid? What's a strong base? What does polar covalent bonds have to do with anything? What do ionic bonds have to do with anything? What does phosphoric acid have to do with anything? Is it important to know the formula for phosphoric acid? You bet. What is a monoproduct, diproduct, triproduct acid? What does that have to do with anything? What is the second ionization of phosphoric acid relative to the first ionization of phosphoric acid, and what would the Ka, relative Kas be? Why would the Ka of the second ionization of phosphoric acid be different from the first Ka? What is a buffer? What is the hydrolysis of a salt? What does the salt of a weak acid do to the pH of a solution? What does the salt of a weak base do? What is a conjugate acid, conjugate base? What is a base and its conjugate acid, etc.? What is a hydrogen donor? What is a hydrogen acceptor? How is that different from an electron acceptor, electron donor? What has a greater dissociation constant, nitric acid or acetic acid? Why is acetic acid so low? What's the structure of acetic acid? Why would that not be as high a dissociation constant as hydrochloric acid? So what does a polar covalent bond have to do with it relative to a completely ionic bond? Okay, so that ends the first part of our review. Now we'll do some problems from each chapter, not including 16 and 19 because we already did a lot of those problems anyway. And again, I will say this, that if you really want to study for your final, I'd say the most important thing to do is to, there's going to be a lot on it relative to acids in terms of this. Acid-base chemistry was the capstone of the course. So I would spend some time actually looking at the lecture for acid-base chemistry and looking at the book problems as well. I had very few hits on YouTube for that chapter, and the grades reflected that. If you can crack acid-base chemistry, I promise you this, you will do very, very well on the final because it contains a summary of many of the concepts that we've learned since Chapter 9. And don't forget to study a little bit of Chapter 8. I know that that's not on the final, but you can't do acid-base chemistry without knowing some of the molecular geometry for things like ammonia, etc. And what does the molecular geometry have to do with hydrogen bonding, with strength of acid, strength of base, etc. So, if you look at my lecture on and my problem sets on acid-base chemistry, you'll see that I'd use a lot of molecular geometry in explaining a lot of those concepts. Okay, so let's do some problems now. That'll be the next part of our review. All right, this is part 2 of our review. Let's do some actual problems. Let's look at some questions. Let's look at some additional material. This is the final exam, and you have been using polyatomic ions for the entire year. You will have to know the common polyatomic ions for the exam. I will not provide a polyatomic ion reference sheet. Please be familiar with the common polyatomic ions. That will also help you speed along the exam. You don't want to be looking up everything that you have to know. Otherwise, you will never get through the exam ever. So here are some of the more common polyatomic ions that I took right from the exam. And you should know these. These are very important for you, and they're very common, with the exception maybe oxalate, but you should know these pretty well by now. Here are the different types of nomenclature, the simple binary nomenclature, ternary nomenclature, Roman numeral stock system, and the Greek system, to name a few. And so you're going to have to know these. You're going to have to know what NaCl is, what CO is, what Fe3PO4 is. You're going to have to know the difference between iron 2 phosphate and iron 3 phosphate, for instance. You have acid nomenclature, which is split up into binary and ternary or oxyacid nomenclature. One uses 2 elements, the other one uses polyatomic ions, and hydrogen always is in the positive component section of the nomenclature. So always remember, it's always going to be HCl, H2SO4. H is always in the positive component when referring to the nomenclature of acids. If it's just a binary acid, it has the prefix of hydro. If it's a ternary acid, we're using a polyatomic ion. There's no prefix. Remember, 8 is ik and ite is us. For the binary acids, it's always ik. Chapter 10 on moles, etc. Let's begin. Now this map you've seen before, and you should write this on your sheet. This is a really nice diagram that I had on the board many times, and it shows you that in order to convert, for instance, from volume to mass, you have to go through moles. Here are simple conversions. This is volume to moles, and then I do moles to volume to get the same answer. So here are some conversions. That's volume mole volume. This is particle mole volume. I put P instead of particles just to conserve space. So look these over. Again, use these as a guide for your cheat sheet. And also ask me to go over problems next week. I'm going to be making videos based on your needs next week in class, and I will go over some of the material and make a video of it. All right, so here's another problem. Here's a volume mole mass problem. I have there's all kinds of problems in here. Don't also forget about empirical formula. We're going to do some problems momentarily. Here's one. The molar mass of a certain gas is 49 grams. What is the density of the gas in grams per liter? Okay, that's a problem. So it's going to go from 49 grams of chlorine per mole to 2.2 grams per liter. That's the density. And here is if the density of an unknown gas, Z, is 4.5 grams per liter at STP, what is the molar mass of the gas? And that's how to do that problem, just as a for instance. So here's another one. Here's 99, and this is from the book problems. What is the significance of the volume 22.4 liters, for instance? And that's, as you know, that at STP, the volume of 1 mole of any gas is 22.4 liters. So that's the significance. Calculate the molecular formula of each of the following compounds. The empirical formula of C2H4O is, and the molecular mass is 88 grams. So C2H4O is 44 grams, 88 divided by 44 is 2. So you divide by the mass, so that's going to be C4H8O2. Because you multiply the molecular formula by 2, each subscript. So it'll be C4H8O2 will be that particular molecular formula. Okay, now, next, the empirical formula is CH, and the molar mass is 104. So 104 divided by 13 will be, whatever that is, probably looks like about 9. I'm guessing 9, because 9 times 12 is 96, so it'll be, no, not 8 times, it would be 8. 8 times 12 is 96. So it'll be 8, so it'll be CHH8 will be the formula there. Okay, next. Next problem is the molar mass is 90 grams. The percent composition is 26.7 for carbon, 71.1% for oxygen, and 2.2% for hydrogen. So what we want to do is we want to convert all, we're going to consider everything is 100 grams. So 26.7 grams, 71.1 grams, 2.2 grams. So what I'm doing first is I'm converting everything to moles. So I have 2.225 moles of carbon, 4.444 moles of oxygen, and 2.2 moles of hydrogen. Now, I'm going to divide 4.444 divided by 2.2, 2.25 divided by 2.2. So I'm going to end up with my mole ratio. So the ratio of oxygen to carbon is 2 to 1, the ratio of oxygen to hydrogen is going to be 2 to 1. So it'll be C2O2. No, C2. It'll be CO2. Yeah, CO2H or CHO2. And then you're going to find the empirical mass, which is 45. So the molecular mass divided by the empirical mass is going to be 2. And so then it'll be C2H2O4. So empirical formula is going to play a big part on the final. So this is important. Maybe you want to write down a particular solution to a problem might be helpful for you. Calculate the percent composition of 2-propanol, which is C3H7OH. And so we have, you find the mass of each divided by the total mass. So the mass of carbon is 36, 3 times 12 divided by 60. 60 is the mass of 1 propanol, and that's the answer to that. So let's review that, because that's going to become very important. So you want to make sure that all of your percentages add up to 100. So it's going to be the total mass of each element divided by the total mass of the particle times 100. So the total mass of the carbon is 36. 36 divided by 60. The total mass of hydrogen, there's 8 hydrogens, so it's going to be 8. 8 times 60. 8 divided by 60. And then the total mass of the oxygen, 16 divided by 60, multiplied by 100, and make sure that 60 plus 13.3 plus 26.7 adds up to 100. At least 99, 98.6, whatever the case may be, but it's very close to 100. Okay, let's look at Chapter 11. Chapter 11, if you remember, is on equation writing. So let's look up some of the problems that we're going to be covering in Chapter 11. What type of reaction are each of the following? So let's see whether or not it's going to be single replacement, double replacement, decomposition, synthesis, and combustion. Calcium reacts with water to form calcium hydroxide and hydrogen gas. So calcium is a lone metal, and a hydrogen gas is a dead giveaway, so it's going to be single replacements. Okay, so that's going to be calcium. So what I'm going to do here is I'm going to actually write out the formula and then try to identify it from writing out the formula equation, a stoichiometric equation, and use that as a way to try to answer the question. And that's really what you should do as well on the final. So the reaction is taking shape. You have calcium plus water yields calcium hydroxide plus hydrogen. Now you're going to have to balance the reaction. And notice I wrote HOH. I find that makes things look a little easier. Now we want to balance the hydroxides and the hydrogen, and it's going to be single displacement, because you have that one element. Producing the hydrogen is often part of these reactions. Now let's look at another reaction. It says tetraphosphorus decaoxide reacts with water to form phosphoric acid. Now there's the tetraphosphorus decaoxide, and I'm going to add water to it, and then I'm going to put phosphoric acid, and then you have to balance the equation. So they don't ask for the type of equation here, but the type would be synthesis, and that's it, balance 164. Again, it's synthesis. Aluminum hydroxide plus hydrogen sulfide forms when aluminum sulfide reacts with water. Now, I didn't write HOH here on this one, but it might be a good idea for you in the future, though, to write HOH. Why? Because you balance the hydrogens and hydroxide, and it's easier to balance the equation. So I have this is double replacement, so I have aluminum plus the hydroxide, and then the hydrogen and the sulfur. So I get aluminum hydroxide plus, this is hydrosulfuric acid. Remember that, that's hydrosulfuric acid, not sulfuric acid or anything like that. So it's going to be 1623. And let's go to Chapter 12, which is stoichiometry, where within a chemical reaction there are inherent proportions that exist that can be used to calculate and predict masses and volumes. Sorry for the arrow out of place. We have aluminum plus oxygen yields aluminum oxide, and we want to balance the equation first, and then we know that the reaction is going to be synthesis. So I have 4 aluminums plus 3 oxygens yield 2 aluminum oxides. So it's going to be 4, 3, 2. And what I want to do is I want to put the stoichiometric masses in. So I'll do that first. So 4 aluminums is 108, and then 4 times 27, and then 6 times 16 is 96, or 32 times 3, and then 204, and the left should equal the right. That's basic mass, conservation of mass. So there's the 583. Remember, it says how many grams of each reactant are needed to form 583 grams of aluminum hydroxide. So my ratio will be 4 aluminums to 2 aluminum oxides, so it's 108 to 204, and that's going to equal x over 583. Solve for x, and that's going to be the answer. So very straightforward. So it's going to be 108 times 583 divided by 204, and that's going to be 309 grams aluminum. And I'm going to do the other quantities, even though it's not asked for. So the oxygen over 2 aluminum oxides, that's going to be 96 over 204, x over 583. Now what you could do is you could say 583 minus 309, and that would also be the answer, but I thought I'd show you how to do it. So 274 grams of oxygen, and those values will equal. Now, and here is Chapter 13. Chapter 13 looks at states of matter. So let's look at a few questions. It says, explain why a gas expands until it takes the shape and volume of its container. So we're looking at states of matter, so how a gas, liquid, and solid respond to the environment. The motion of particles in a gas is constant, random, and rapid. So it doesn't have a definite shape, as what you may have learned when you were younger. This is just an extension of that. The motion of particles in a gas is constant, random, and rapid. Use the drawing to explain how gas pressure is produced. Gas pressure is a result of collisions on the wall of the container, and that's it. That's really all it is. You also want to ask yourself, what is the relationship between collisions, pressure, and temperature? Are they direct or are they indirect? Look at Gay-Lussac's law. I'm going to spend some time on this chapter because it is the underpinnings of gas laws and much of the dynamics that occurs in the rest of chemistry. The book says, to answer the question, gas pressure is the result of the collisions of gas particles with the container walls. Sounds familiar. So, what is the relationship between these collisions and temperature as well? What pressure in kilopascals and in atmosphere does a gas exert at 385 millimeters of mercury? There are the calculations, and there are the answers. So it's going to be 51.3 kilopascals and 0.507 atmospheres. The pressure at the top of Mount Everest is 33.7 kilopascals. Is that pressure greater or less than 0.25 atmospheres? It is greater than 0.25 atmospheres, but not by much. Briefly describe the assumptions of kinetic theory as applied to gases. So this will be a little bit more of an essay question. A gas is composed of tiny particles whose motion is rapid, constant, and random. Collisions between particles are perfectly elastic. Key concept: use kinetic theory to explain what causes gas pressure. Gas pressure is the result of simultaneous collisions of billions of rapidly moving particles with an object. Key concept: how is the Kelvin temperature of a substance related to the average kinetic energy of its particles? The Kelvin temperature is directly proportional to the average kinetic energy of the particles. Number 6. Convert the following pressures to kilopascals. Remember, kilopascals involves newtons, and a pascal is Newton over meter squared, so that's going to be SI units. The first one is 96 kilopascals. So how did you get that? Well, 1 atmosphere is 101.3, so you divide by atmosphere and multiply by kilopascals, 101.3 kilopascals in an atmosphere. So you multiply through and you get 96 kilopascals, which is almost 1 atmosphere. 45 millimeters of mercury, you're going to divide through by millimeters, multiply by 101.3, and you get 6 kilopascals. And that's the answer. Again, very simple conversions. Make sure you can do them in your sleep. A cylinder of oxygen gas is cooled from 300 Kelvin to 150 Kelvin. By what factor does the average kinetic energy of the oxygen molecules in the cylinder change? By 1/2. Remember, you have to convert to Kelvin before you can do these kind of calculations in gas laws. What factors help determine the physical properties of liquids? What factors help determine the physical properties of liquids? The interplay between the disruptive motions of particles in a liquid and the attractions among the particles. Key concept again. In terms of kinetic energy, explain how a molecule in liquid evaporates. Remember, key concepts are definitions. A molecule with a certain minimum kinetic energy can escape from the surface of the liquid and vaporize. Number 10. Key concept again. A liquid is in a closed container and has constant vapor pressure. What is the relationship between the rate of evaporation of the liquid and the rate of condensation of the vapor in the container? Okay, don't forget that it has to be a closed container. So it says a liquid is in a closed container and has a constant vapor pressure. Okay, that's important. Rate of evaporation of the liquid equals the rate of condensation of the vapor. It's going to reach an equilibrium state. Another key concept: what condition must exist for a liquid to boil? The vapor pressure and the atmospheric pressure must be in equilibrium with each other. Particles throughout the liquid must have enough kinetic energy to vaporize. So it has to be able to beat the atmospheric pressure. Explain why the boiling point of a liquid varies with atmospheric pressure. Boiling occurs when the vapor pressure of the liquid equals the external pressure. If the atmospheric pressure changes, the boiling point will change. Remember, it's going to try to open up. It's going to try to form a bubble, but it can't if the atmospheric pressure is too great. All right, here are some curves: vapor pressure and temperature. The vapor pressure of ethanoic acid is 27 kilopascals. Chloroform is 80 kilopascals, and ethanol is 50 kilopascals. And these are the curves. And then the boiling points would be listed there, would be 52, 62, and 76. That's where the boiling points would occur. And there are the answers: 76, 52, and 62. You just go up the vapor pressure scale, and then where it hits the line, and then down to the temperature, and those are the boiling points. So it might confuse you because you're not going up to 101.3 kilopascals where the atmospheric pressure is. Well, it's where the vapor pressure equals the atmospheric pressure. Water boils at 100 degrees Celsius because its vapor pressure is equal to 101.3 kilopascals. So at 101.3 kilopascals, ethanoic acid, chloroform, and ethanol have already boiled. So that's why they have very low boiling points because of that, and because of the shape of their curve. Okay, explain how evaporation lowers the temperature of a liquid. Why is it a cooling event? Well, When the molecules with the highest kinetic energy escape from the liquid, the average kinetic energy of the remaining particles is lower, and therefore the temperature decreases. So you're taking heat away from the molecules that are remaining, thereby lowering the temperature. In general, how are the particles arranged in solids? Very neatly, essentially. Particles in solids are packed tightly together in an orderly arrangement. The locations of the particles are fixed. It has very low entropy, but you will learn that later in another chemistry course if you continue with chemistry. What does the shape of the crystal tell you about the structure of a crystal? The shape of the crystal reflects the arrangement of the particles within the solid. How do allotropes of an element differ? The famous one is graphite and diamond. Allotropes are different molecular forms of the same element in the same physical state. What phases are in equilibrium at a substance's melting point? The liquid and solid states are in equilibrium. Gaseous states is in the boiling point, gaseous and liquid. How do the melting points of ionic solids generally compare with those of molecular solids, such as water? Ionic solids generally have higher melting points than do molecular solids. Sodium chloride is a great example. What is the difference between a crystal lattice and a unit cell? A unit cell is part of the lattice. A crystal lattice is a repeating array of unit cells. Number 21. Key concept again. What properties must a solid have to undergo sublimation, such as carbon dioxide? Sublimation occurs in solids that have vapor pressures that exceed atmospheric pressure at or near room temperature. Key concept. What do the curved lines on a phase diagram represent? Essentially boundaries. The lines show the conditions of temperature and pressure at which two phases exist in equilibrium. Two phases meaning boundaries. Describe one practical use of sublimation. Separation of materials, it can happen. We used to do that when we used to make caffeine. Freeze-dried coffee, dry ice as a coolant, air fresheners, separating mixtures, and purifying substances, to name just a few. What does the triple point on a phase diagram describe? The triple point describes the only set of conditions at which three phases can exist in equilibrium. That's a definition. It's a very good definition. Using figure 13.15, estimate the boiling point of water at a pressure of 50 kilopascals. 50 kilopascals, it says the boiling point. So it would be liquid to vapor, about halfway. So we're going about, I don't know, it's hard to say with this particular graph. Let's see what the book says in a minute. But if you look down at the triple point occurs at very low pressures in water and very cold temperatures. So around 0 atmospheres and really cold, around 0 degrees Celsius, you're going to have sublimation of water, and it's called lyophilization. To answer the question, however, it's about half, I'd say, yeah, 60 degrees Celsius. Very difficult to read the scale without additional graduations, but 60 looked about right. What is meant by an elastic collision? An elastic collision is a collision that you don't lose energy. In elastic collision, energy is transferred between particles. So in other words, the particle's going to lose energy, but then it's going to gain it right back because of another collision. So you get a net zero loss. Which of these statements are characteristic of matter in the gaseous state? Gases fill their containers completely. The answer is yes. It's fairly straightforward. Next, gases exert pressure. I certainly hope so. And it's proportional to temperature. Gases have mass. They do. It's matter. All matter has mass. So that's true. The pressure of a gas is independent of its temperature. Not true. Gay-Lussac's law proves that. Gases are compressible. Yes, correct. There's a lot of empty space in there that can be compressed. The gases can be compressed into. The distance between particles in a gas are relatively large. Yes, relative to solids and liquids. Correct. List the various units used to measure pressure and identify the SI units. Pascals is SI, millimeters of mercury, which they use in the United States quite often, and atmospheres, where the pascals are newtons per meter squared. Newtons are SI, meters are SI, so meters squared would be correct, and newtons per meter squared would be equally correct. Change 1656 kilopascals to atmospheres, and that would be 16.35 atmospheres. 16.35 atmospheres, approximately 100 pascals per atmosphere. Convert 190 millimeters of mercury to the following. So it's going to be 760 millimeters of mercury. Kilopascals, it's going to be about, I don't know, a quarter, 25 kilopascals, it's about right, 25 kilopascals. I'm not showing you the calculation here. It's fairly simple at this point. Atmospheres, so again about a quarter of an atmosphere, 0.25 atmospheres, a quarter. C would be approximately, oh, no C. Explain the relationship between the Kelvin temperature of a substance and the kinetic energy of its particles. The Kelvin temperature is directly proportional to the average kinetic energy. Is proportional to the average kinetic energy. Remember, these are the underpinnings of gases. So it's critical that you have a good understanding of this. How is the average kinetic energy of water molecules affected when you pour hot water from a kettle into a cup at the same temperature as the water? Well, you're going to lose less energy, certainly. I like to rinse my teacup out with hot water before I put in coffee. If the temperature does not change, the average kinetic energy is not affected. Your coffee stays hot longer. What does the abbreviation STP represent? It represents standard temperature and pressure. STP stands for standard temperature and pressure, 0 degrees Celsius, and 101.3 kilopascals, or 1 atmosphere. Don't forget, it should be 273 Kelvin. What is the significance about the temperature absolute zero? At absolute zero, the motion of particles would theoretically cease. The average temperature of the universe is actually about 2 Kelvin, mostly cold, empty space. Stars don't radiate energy, heat into space. They radiate light. By what factor does the average kinetic energy of the molecules of gas in an aerosol container increase when the temperature is raised from 27 degrees Celsius to 627 degrees Celsius? The average kinetic energy triples. So you have to change it to Kelvin, and then it's very plain to see once you change it to Kelvin. Now let's do gases, is chapter 14. Calculate the ratio of the velocity of helium atoms to the velocity of neon atoms at the same temperature. So this is Graham's law of diffusion or effusion. Make sure you know the difference between diffusion and effusion. It will be very helpful in answering these questions. So it's going to be the velocity of A over the velocity of B equals the square root of the molar mass of B over the molar mass of A. So you want to pick the one that gives you a whole number first. So that's going to be 20 over 4, and that'll be root 5, which is about 2.5-ish. So it'll be 2.25. So certainly not 2.5, but greater than 2 and less than 3. So it'd be 2.25. Next. Calculate the ratio of the velocity of helium atoms to the velocity of fluorine molecules at the same temperature. Notice it says fluorine molecules, not fluorine atoms. It would be 19 over 4 if it were fluorine atoms, but it's actually root 38 over 4 for molecules. Remember, helium is monoatomic, so the root 38 over 4 is 3.08, so it would be 3.08 to 1. Now don't forget, that's the reciprocal, so in other words, read it carefully. It says rate A is helium, B is fluorine, because it's the rate of A over B equals the square root of B over A. So the rate of A over B, so it's going to be helium is 3.08 to 1 fluorine. So don't get confused by that. Read it as is stated. How does the kinetic theory, explain the compressibility of gases? How does kinetic theory explain the compressibility of gases? Gases are easily compressed because there is a lot of space between the particles. Use this description to answer questions 65 and 66. A teacher adds 1 milliliter of water to an empty metal soda can. The teacher heats the can over a flame until the water boils and then quickly plunges the can upside down into an ice water bath. The can immediately collapses inward as though crushed in a trash compactor. Use kinetic theory to explain why the can collapsed inward. Use the kinetic theory to explain why the can collapsed inward. Boiling the water fills the can with steam. When the can is plunged upside down into ice water, the steam is trapped and rapidly condenses, reducing gas pressure inside the can. The walls of the can are not strong enough to withstand the comparatively high atmospheric pressure, which crushes the can. If the experiment were done with a dry can, would the results be similar? The results would be much less dramatic. The change in volume and in internal pressure from heated air to cold air is much less dramatic than when steam, a vapor, condenses to form a liquid. Why do aerosol containers display the warning, "Do not incinerate"? High temperatures increase the pressure of the contents of the container and may cause it to explode. The manufacturer of an aerosol deodorant packaged in a 50 milliliter container plans to produce a container of the same size that will hold twice as much gas. How will the pressure of the can in the new product compare with that of the gas in the original container? Well, I'm going to have literally twice the number of particles, so the pressure will double. The pressure will double. Next, why must Kelvin temperatures be used in calculations that involve gases? Temperatures measured on the Kelvin scale are directly proportional to the average kinetic energy of the particles. Celsius temperatures are not. So you always have to change things to Kelvin. Explain how using a pressure cooker reduces the time required to cook food. Because as you increase pressure, you increase temperature. So the food is actually cooking at a higher temperature. The water boils at a higher temperature, which speeds the cooking process. Also, water is wonderful for cooking. It delivers the heat very quickly. When it touches it, it's very good. The ratio of two variables is always a constant. What can you conclude about the relationship between the two variables? By the way, the water will cook, even though water is not a good heat transfer, it's better than air as opposed to cooking in the oven, so relatively it's quicker. The variables are directly proportional. A 3.5 liter gas sample at 20 degrees Celsius and a pressure of 86.7 kilopascals expands to a volume of 8 liters. The final temperature of the gas is 56.7. The final pressure of the gas is 56.7. What is the final temperature of the gas in degrees Celsius? So this is a combined gas law problem, PV over T equals PV over T. I want to plug in the values. The pressure, P1, is going to be 86.7 kilopascals. The V that goes with that pressure is 3.5 liters. The temperature is 293 Kelvin. That goes with that set of conditions. Now we want the new set of conditions. There's the pressure, 56.7 kilopascals, so I'm reducing the pressure. 8 liters, but I'm increasing the volume. And then I want to calculate the temperature in degrees Celsius. So there's the equation, PV over T equals PV over T. Now I'm going to look at my set of values and plug in. So I have everything all plugged in. Notice that things are in Kelvin, and I want to calculate Celsius. So when I do the calculation, I find out, I just simply multiply and divide. I get 438 Kelvin, and then which equals 165 degrees Celsius. So it's just plug and chug. Now, chapter 15, which is water and aqueous systems. You'll remember we did a lot of work with that, with colloids and suspensions and solutions, etc. Are all liquids soluble in each other? Explain. No. Nonpolar molecules do not dissolve in polar molecules, and vice versa. Write equations to show how these substances ionize or dissociate in water. Well, ammonium chloride will dissociate into NH4 plus 1 and Cl minus 1. So that's the dissociation of ammonium chloride. And you'll see that it does the ions. If something doesn't dissociate well, it doesn't dissolve well, unless there's a lot of hydrogen bonding inherent within the molecule, such as sucrose or glucose. This is copper 2 nitrate, so that's going to dissociate into copper plus 2, and it will do the nitrate, which is NO3, which is minus 1. You'll see that that NO3 should be the subscript 3 should be there, but that's okay, you understand that. And then you have acetic acid, which we'll see in chapter 19 quite a bit, and that's going to be H plus, and it's going to be C2H3O2 minus 1 charge. So then the next one is going to be D, is going to be mercury 2 chloride, and that will go into mercury plus 2 and chlorine negative 1. You're already seeing that the chapter 9 and chapter 11 are very important in doing this chapter so far, especially with number 66. You have to be able to write balanced equations and know your nomenclature. Name these hydrates and determine the percent by mass of water in each. This is going to be sodium carbonate monohydrate, and the way you calculate the percent of water is you find the total mass of the particle, and 2 sodiums, 1 carbon, 3 oxygens, 2 hydrogens, another oxygen, and then you say the total mass of water, which is 18 in this case, divided by the total mass of the particle times 100. The next one is magnesium sulfate heptahydrate, and there's the percentage. How many grams of copper 2 sulfate pentahydrate would you need to measure in order to have 10 grams of anhydrous copper 2 sulfate? If 15.6 grams of copper 2 sulfate. 15.6 grams of copper 2 sulfate. Now for chapter 16, that's going to be solution chemistry, and that's going to be how many moles of ammonium nitrate are in 335 milliliters of 0.425 molar ammonium nitrate. There's the equations. There's the expanded molarity equation. Plug in because you're given the liters, so you can get rid of the denominator there, so it's just moles per liter. And then what you do is, so as you remember, molarity is moles per liter of solution. So you're given the milliliters, which is going to be 0.335, and you have the molarity, so you're going to multiply the two together. The liters times the molarity will equal the moles. So it's going to be 0.425 molar times 0.335 liters, and that's going to be equal to X moles. So it's going to be approximately X moles equals 0.142 moles exactly. How many moles of solute are in 250 milliliters of 2 molar calcium chloride? How many grams of calcium chloride is this? Well, there's the equation. Molarity M equals moles over liter equals mass over atomic weight and over milliliters over 1,000. So I'm plugging in because you're given milliliters, which I'm changing directly to 0.25 liters, and you're given the molarity, and you multiply the molarity times the liters, you get 0.5 moles. So it's going to be a half a mole of the compound. So 1/2 a mole of calcium chloride, which is 110 atomic mass units per mole, is 55 grams. How could you prepare 250 milliliters of 0.2 molar NaCl using only a solution of 1 molar NaCl and water? All right, here is the solution. Instead of bringing it on a little bit of the time, I have the solution, and the equation for dilution is M1 times V1 equals M2 times V2. Now, I'm plugging in. My first conditions are going to be 0.2 molar and 250 milliliters. And then my second conditions are going to be 1 molar and V2. I'm solving for V2. Now, what you can do, and you don't have to, you can keep it in milliliters, but what I did was, before I actually plugged in, I changed 250 milliliters. You don't really have to do that, but I'm showing you that you can or you may or may not. So that's going to be 0.2 times 0.250. So it's going to be 0.2 molar times 0.250 liters divided by 1 molar equals 0.05 liters, which translates to 50 milliliters. Now, if you kept it as 0.2 molar times 250 milliliters divided by 1 molar, you would get 50 milliliters directly. So it depends what they're asking for. It depends what you're given. So as long as you're consistent and you make the appropriate changes before or after, then you're not going to make a mistake. Now, the actual directions for adding the ingredients are: use a pipette to transfer 50 milliliters of the 1 molar solution to a 250 milliliter volumetric flask. Then add distilled water up to the mark, so that what you have is you have the solute. You put that in first. You put the ingredients in first, and then you dilute it up to the mark. So what you need to do is you have to remember that you need the entire solution has to have a molarity. So it's going to be 1,000 milliliters of solution, 100 milliliters of solution. So if you add your 50 milliliters first, and then you dilute it up to 250 milliliters using a 250 milliliter volumetric flask, you'll end up with 0.2 molar solutions, 0.2 moles per 250 milliliters of solution. Very important distinction. Calculate the molarity of a solution containing 400 grams copper 2 sulfate in 4 liters of solution. So you have to change 400 grams of copper 2 sulfate to moles. That's the first thing you're going to do, and then you're going to divide it by 4 liters, and that's going to be the molarity, because you have to come up with it per liter. So it's going to be 0.627 molar copper 2 sulfate solution. How many grams of sodium fluoride are needed to prepare a 0.4 molal sodium fluoride solution that contains 750 grams of water? Now, I have everything mapped out for you here. The equation for molality is moles over kilogram, which equals the mass of the solute divided by the atomic weight if you need to expand the equation, divided by the grams of the solvent divided by 1,000 if you need to expand the denominator. Okay, so it's going to be a sodium fluoride solution. So it's going to be the mass of sodium fluoride divided by 42 divided by 0.750 kilograms. I automatically change 750 grams to kilograms. So then what you're going to do is you're going to cross multiply 0.4 molal times 0.750 kilograms. Alright, so that will give you 0.4 molal times 0.750 kilograms, and then you're going to cross multiply again. So that will give you 0.4 molal times 0.750 kilograms times 42 equals the mass. So the mass will equal 12.6 grams. So now, when you make this, you're putting the water in first, and then you're putting the solute in. So that's a little bit different from molarity. This is molality. In molality, you put the solvent in first, then you put your solute in, where in molarity, you put your solute in first, and then you put the water in up to 1 liter. All right, the next one says, what is the freezing point depression of an aqueous solution of 10 grams of glucose? Glucose does not dissociate in 50 grams of H2O. In 50 grams of H2O. I have everything worked out for you. Notice that in some of the problems I multiply Kf by the number of particles, but glucose doesn't dissociate, so it's just going to be Kf times the molality, and I'm going to plug in for the various values. I have 10 grams over 180, and then 50 grams over 1,000 grams, and that will give the mass of the solution. So I have the mass of material divided by 180, which is the atomic weight of glucose. So that will give the number of moles. So it's the number of moles over the number of kilograms of solution so far. So now let's take it from that point. So 10 divided by 180 divided by 0.05, that's the mass of solvent, times 1.86, which is the constant for freezing point depression. So the freezing point depression is going to be 2.1 degrees Celsius. So the freezing point will be negative 2.1 degrees Celsius. What is the boiling point of a solution that contains 1.25 moles of calcium chloride in 1,400 grams of water? Notice I have everything worked out. So let's take a look at it carefully, spend some time with it. Okay, we see that we have the boiling point elevation equals the number of ions. I have the number of ions now. We call that N. Some textbooks call it N. Then times the boiling point constant times the molality. So I'm given moles and mass, moles of solute and mass of solvent. So it's just going to be 3, because calcium chloride, CaCl2, breaks down to 3 ions, times 0.512 times the quantity 1.25 divided by 1.4. The boiling point elevation is 1.37, therefore the new boiling point is 101.37, and that concludes the review for Chapter 16. Alright, Chapter 19, Acid-Base Chemistry. This should be most fresh on your mind. I strongly recommend looking at some of the videos on acid-base chemistry to help you with this. It's a capstone for the course. You will need lots of concepts earlier in the semester in order to answer these. We're going to run through this very quickly. and let's see how you do. How many milliliters of 0.45 molar HCl will neutralize 25 milliliters of 1 molar KOH? Notice that it's going to be 1 to 1. So you've got to figure out how many particles there are in 25 milliliters of 1 molar KOH. So if you know specifically how many particles, and you know that it's in moles, then you take the same amount of moles of HCl. So what volume will have that many moles? What volume of HCl will have the amount of moles that is given in 25 milliliters of 1 molar KOH? So 1 mole of KOH per 1,000 milliliters, that's what it is. It's molarity of 1 over 20 equals X over 25. And so that's going to be 0.025 moles. So I need 0.025 moles. So what volume of a 0.45 molar solution of HCl has that many? And it's 56 milliliters. So in 56 milliliters, I have 0.025 moles. And that's the answer to the question. What is the molarity of phosphoric acid if 15 milliliters is completely neutralized by 38.5 milliliters of 0.150 molar NaOH? And this is the reverse problem that we just did. So it's going to be 0.150 moles per 1,000 milliliters. How many moles in 38.5 milliliters? Well, it's 0.0058 moles. Now what I want to do is, I want to say, okay, 0.0058 moles of KOH is equivalent to, so remember, we're looking at a triprotic acid. We need a triprotic acid. So if we're going to be neutralizing it with KOH, and each particle of KOH yields up 1 OH, we're going to need 3 times that many because we have a triprotic acid. So let's look at this very carefully before we proceed. Look, the problem says, what is the molarity of phosphoric acid if 15 milliliters is completely neutralized by 38.5 milliliters of 0.150 molar NaOH? In that volume, I have 0.0058 moles. That's how many particles of OH I have available because it's KOH, 1 K per 1 OH. So, but I need 3 times that much because for every particle of phosphoric acid, I have 3 particles of hydrogen, H+. So I'm going to need 3 times that amount. So how much is it's going to be? So 0.0058 moles of KOH is equivalent to 0.00193 moles of H3PO4 because it says that it was neutralized by 0.058 moles of KOH. It was neutralized by that much. That's how much I used. So, and then it says, well, okay, I have 15 milliliters of the KOH. I'm sorry, 15 milliliters of the phosphoric acid. So, I'm going to calculate the number of phosphoric acid molecules I have in there. They're not really molecules, but let's say that particle. All right. Well, I need enough KOH to neutralize 3 times whatever I have in there. So I'm going to need 1 OH. 1 OH is going to, 3 OHs is going to neutralize 1 particle of phosphoric acid, right? So if I use 0.0058 moles, I did 1/3 that many phosphoric acid molecules. A little confusing, but think of count them. Think of the number of each particle present. You got to do it in terms of numbers of particles. So the total amount of OH I have available is 0.0058. That's only enough to do 1/3 in terms of equivalence of phosphoric acid. So 0.0058 moles only allows me to do 0.00193 particles of phosphoric acid. So 0.000193 moles of phosphoric acid. Okay, that's how much phosphoric acid I have. So how many, how many moles are there? How many moles are there in that much phosphoric acid? And so I say 0.00193 moles divided by 15 equals x over 1,000. Now I solve for x. Let's see what we get. So the answer is 0.129 moles per 1,000 milliliters. So I can only do, I can only do 0.129 moles. I can only do 0.129 moles of phosphoric acid. So the molarity of the solution is only 0.129 moles in 15 milliliters. So it's got to have a molarity of 0.129 molar. Calculate the pH of a 0.010 molar solution of sodium cyanide. The Kb of cyanide is 2.1 times 10 to the negative 5. Now, sodium cyanide is the salt of a weak acid. Cyanic acid is actually a weak acid. So the solution is going to be basic. So that's why you're using a Kb. You're going to produce hydroxide ion concentrations. So this is the way you'd set it up. You'd say the molar concentration of hydroxide times the molar concentration of the HCN divided by the molar concentration of the CN anion, or sodium cyanide solution, and the concentration of the HCN and the OH is going to be equal, because it's going to be 1-to-1. We only do 1-to-1. We only have one either hydroxide produced or one H plus produced. We only do one at a time. So the numerator, the product of the numerator is going to be a square, because the HCN and the hydroxide are equal. So it's going to be x squared divided by the original concentration of the sodium cyanide equals the Kb. So let's look at it from that point of view. So it's going to be the square root of the product 0.010 molar times 2.1 times 10 to the negative 5th. So that's going to be, you're going to take the square root of that, and that's going to be the OH concentration. Now I can say 1 times 10 to the negative 14, which is the Kw, divided by the OH concentration equals the H ion concentration. And then I could say the negative log of the H ion concentration is going to be 10.66. And that makes sense because it is basic. It is basic. Show that for any conjugate acid-base pair, Ka times Kb equals Kw. And also the ion, the H ion times the OH ion also equals Kw. And the way you know that is if you say, okay, you have Ka and Kb, those are the corresponding expressions. Everything cancels out, and you're left with the molar concentration of the H ion times the molar concentration of the OH ion. And that's proof of that. So that's it. Use the cyanic buffer to illustrate how a buffer system works. Show by any means of equations how the pH of the solution can be kept almost constant when small amounts of acid or base are added. So you can see if I add a base there, I'm going to produce water and the anion, and if I add an acid, I'm going to produce the acid portion, the HOCN. So that's proof by equations. Suppose you slowly add 0.1 molar NaOH to 50 milliliters of 0.1 molar HCl. What volume of NaOH must be added for the resulting solution to become neutral? Okay, notice the molarity is the same. So that's the equation. HCl plus NaOH is salt and water, and it's 50 milliliters of that. The pH equals 7 when the H ion concentration and the OH concentration are equal. Because HCl is a strong acid that supplies 1 hydrogen ion per formula unit, and NaOH is a strong base that supplies 1 hydroxide ion per formula unit, H plus equals OH minus when equal volumes of solutions of the same molarity are combined. Notice that's molar concentrations of those. All right, what is the molarity of a sulfuric acid solution if 80 milliliters of the solution reacts completely with 0.42 grams of sodium carbonate? Okay, here's the reaction. Here are the stoichiometric masses that I need because I'm comparing the sulfuric acid with the sodium carbonate. That's the arrow. I am going to need 0.424 grams of sodium carbonate. So the first thing I'm going to do is I'm going to perform a stoichiometric operation and find the mass of sulfuric acid I will need to combine with 0.424 grams of sodium carbonate. So I set it up with the constant ratios and I solve for x, cross multiply and divide, and I get 0.392 grams of sulfuric acid. Now, I say 0.392 grams of sulfuric acid over 80 milliliters of sulfuric acid solution. So that's what I have. Okay, that's what I have. Now, what do I have to do next? Well, I'm going to have to change the 0.392 grams of sulfuric acid to moles, divide by 98, and you cancel out, and you get the moles of sulfuric acid are going to be 0.004 moles. So I have 0.004 moles of sulfuric acid over 80 milliliters of solution. So if I have 0.004 moles per 80 milliliters, how many do I need per 1,000 milliliters? So, and that will give me the molarity right away, because molarity is per 1,000 milliliters or 1 liter. So, cross multiply, divide, my molarity is 0.05 molar, 0.05 moles per liter. So that's the molarity of the sulfuric acid solution. Next, household bleach is a solution of sodium hypochlorite, NaClO. It is considered a hazardous solution because it is basic and because it contains the active bleaching ingredient ClO. What is the hydroxide ion concentration, molar concentration, in an aqueous solution that is 5% sodium hypochlorite by mass? What is the pH of the solution? The density of the solution is 1 gram per milliliter, and the Ka is 3.5 times 10 to the negative 8th. So, now let's do it. So I have 5 over 100 grams of each, and I know that molarity is per 1,000 milliliters of solution. The density is 1, so I can automatically change 100 grams to 100 milliliters. And I know that the denominator is per solution, and so is molarity, so I could just multiply it by 10 over 10. So that'll be 50 grams of sodium hypochlorite per 1,000 grams or 1,000 milliliters of solution. So now I have to change 50 grams of sodium hypochlorite. I have to change it to moles. Notice I just made the switch from 1,000 grams to 1,000 milliliters. Now I have to change 50 grams of sodium hypochlorite to moles. Now I'm going to simply divide through, but let's take a break here to get the Kb. Why do I need Kb? Because Sodium hypochlorite is the salt of a weak acid. The salt of a weak acid will produce a basic solution, so I need Kb, not Ka. So it's going to be 1 times 10 to the negative 14 divided by 3.5 times 10 to the negative 8, and that's going to be the Kb. So the Kb solution, the Kb constant will be 2.857 times 10 to the negative 7th. So that's going to be the Kb. Now I'm all set. Now I have to convert the 50 grams of sodium hypochlorite into moles. So there's the 50 grams of sodium hypochlorite, and I'm going to convert that to moles per 1,000 milliliters of solution, which will give me the molarity. So 50 divided by 74.4 grams, and that's going to be equal to approximately 0.67-ish, 0.67 moles approximately. So wait for it, 50 divided by 74.4 is going to be, I'm leaving quite a bit of time between slides here, 0.672. You see that 50 over 74.4 is about 2/3. So the molarity of the solution will be 0.672 molar. That is the molarity of the solution. Now I want to understand that for every hypochlorite in solution, I'm going to produce for every particle of hypochlorite, I'm going to produce one OH and one hypochlorous particle. So I know that the numerator there is squared. It's going to be x squared if x equals the hydroxide ion concentration. So it's going to be 0.672 times the Kb. Remember that the HClO and the OH concentration are the same. We did that. And therefore, I'll just let this run a little bit, and you could take notes or try to understand this, and we'll see what happens. Let me just let this run for a minute. You know, you could stop and rewind if you didn't understand something. Okay, that's the Kb. That's the Kb expression, and I'm going to substitute in an OH for HClO. I hope you understand why. Remember, they're equal, so I can make a substitution and say OH -1 molar concentration squared over ClO molar concentration, and I can plug in for the ClO molar concentration and the Kb, then take the square root of that, and that's exactly what I'm going to do. And it says what is the OH ion concentration and what is the pH of the solution. Okay, I need to know both. So take the square root of the product of 2.857 times 10 to the negative 7th quantity times 0.672, and you get Kb is very small, so the molarity of the reaction does not have to be subtracted from. In other words, I don't have to subtract off the concentration of the hydroxide that I'll get in terms of some unknown. It's not a big deal. I wouldn't worry about it. We're going to do buffer systems next week or tomorrow. There's the restatement of the question. Look that over, and then we'll get back to it. I just wanted to, before I started to calculate it, I wanted to restate the question. All right, here we go. So let's do the math. And now we're going to get the OH concentration, the OH minus concentration, by taking the square root of the product. And we get 4.4 times 10 to the negative 4th molar. Now I could find the negative log of that and get the pOH, and then say 14 minus the pOH is going to equal the pH. Honestly, I don't remember what I did. You can either do that, or yeah, that's what I did. Or like the last problem where we said Kw divided by K divided by OH equals the H ion concentration. So now the pOH concentration, I'll let this play out. Try to do it yourself. This is the last problem for acid base. I'm going to add a few slides to this and it's going to be on equation writing, just a few, not much. I just want to do a few more problems on Chapter 11, equation writing, and then we'll be finished the review. So the pOH is 3.36. 14 minus 3.36 will equal the pH, and then I will restate that at the bottom of the slide, if I recall correctly. So, the pH is going to come up in a moment. I'm going to subtract 3.36 from 14, so you'll get something. 10.64. So, the answer to the question is, the molar hydroxide ion concentration is 4.4 times 10 to the negative 4 molar, and the pH of the solution will be 10.64, and that makes sense because it is the salt of a weak acid. Okay, coming up, a little addition to Chapter 11 review. All right, this is supplemental Chapter 11 questions, a few additional ones. I didn't think I paid enough attention to it earlier. Balance these equations. Let's look and see what the coefficients will be. All right, that's the first equation, and the coefficients will be 6,619. So that's the ratio. Next is sodium plus water. Notice I wrote HOH yields sodium chloride plus hydrogen, 2,2,2,1 in that order. Identify the type of chemical reaction. First one is synthesis. Next one is decomposition. The next one is single replacement. The next one is combustion. The next one is single replacement. And the next one is double replacement. Okay, let's continue. Write the net ionic equation for the following reaction. Okay, that's going to be as it is. Easy. Don't forget to balance it. Indicate by simple equations how the following substances ionize or dissociate in water. This is actually Chapter 11. That will be NH4 plus Cl minus. Next, Cu plus 2 and NO3 minus 1. Okay. This looks familiar, but either way. So it'll be H plus NO3 minus. This will be, I think that might be it. And there's another one. Indicate by simple equations the following dissociation. Okay, that's going to be similar to Chapter 19. And then that one's going to be Na plus and SO4 minus 2. Don't forget to balance it. And that will be Hg plus 2 and Cl minus. Don't forget to balance it. Okay, and that concludes everything. That is your review. Good luck on your final exam, and goodbye.